Thanks.
Thank you. Thank you so much.
So good evening and good morning to everyone joining us from around the world. So on behalf of the International Union of Pure and Applied Physics, so the IUPAP and the UNESCO, it's my great pleasure to welcome you to this 6th edition of this IUPAP UNESCO International Colloquia on Physics for Society, entitled The Challenge and Opportunities of Getting to Net Zero Greenhouse Gas, those famous GHG emission. So this is a presentation today by the Laureate of the Nobels, Professor Stephen Chu. So we're very honored to have him with us. So my name is Christine Dove and I work at the European Spallation Source in Lund, in Sweden, and I share the IUPAP Working Group on Particle Accelerator for Science and Society. So this colloquium series was created to highlight how physics can contribute to addressing some of the most urgent challenges of our time. So at the moment when science is advancing rapidly, it's also being called upon to help guide solutions from energy, climate, technology, and sustainable development. So through this series, we aim to bring together scientists, policymakers, international organizations, and the global audience to strengthen dialogue across discipline and to broaden, to connect the fundamental research with the societal impact. So this initiative is built on the partnership between the IUPAP, representing the global community of physics, and the UNESCO, the United Nations agency dedicated to advancing education, science, and culture. So together we share a convincing that, and we're all really convinced by the science, it's not only a driver of innovation, but also a shared global language for cooperation and for building a sustainable future. So the series was launched in 2025 within the framework of the International Year of Quantum Science and Technology. So it's the first cycle, and we have explored how advance in physics relate to the technology and how it can contribute to this United Nations Sustainable Development Goal. So all the recording of the previous session are available on our website, and we warmly invite you to explore them. So now, looking ahead, so this colloquium series will become increasingly aligned with this International Decade of Science for Sustainable Development, 2024, 2036, or 2033. We'll see how it goes. But a decade where the UN initiative recognizes that addressing the major challenge of our time will require stronger international scientific cooperation, deeper interdisciplinary, and a close link between the scientific knowledge and the policy and the politic. So our ambition is to create a living forum where science, policy, and society meet, exchange ideas, and help shape this pathway forward together. So today we are deeply honored to welcome Professor Stephen Chu, Nobel laureate in physics and former United States Secretary of Energy, and one of the most leading voices in this intersection of physics, energy system, and the climate action. So following the lecture, we will hold a question and answer session, and we warmly encourage your participation. So please submit your question through this talk after using this Q&A function. So a selection of the question will be discussed to ensure that we will interactively have the audience participation. So before we begin, I would like also to acknowledge the colleagues that are here, in this panelists who will help guide today's event. So Dr. Amal Kasri, who is the Chief Basic Science Research Initiation and for the Innovation Engineering at UNESCO. Professor Sylvina Pons-Dawson, the President of the IUPAP. Our Professor Laura Green, who is the Chief Scientist at the National High Magnetic Field Laboratory, in Florida State University. And also behind the scene organizing this event, Jing Zhao, who is the coordinator of the UNESCO Global Quantum Initiative, and Dr. Irvi Girmhill, who is from the University of Wits in South Africa. So now it's my great pleasure to invite Dr. Amal Kasri to offer this opening remark for this UNESCO engagement on this initiative. So this decade of international science for development and sustainable development. So Amal, the floor is yours.
Thank you. Thank you so much, Christine, for this introduction. And Professor Shu, great to have you with us here. We met many years ago. I don't think you remember me, but really a pleasure to have you here today. Dear Professor Shu, dear colleagues and participants, it's really a great pleasure to welcome you to this IUPAP UNESCO International Colloquium on Physics for Society. UNESCO is very pleased to continue this collaboration with IUPAP, which has provided an important platform to highlight the role of physics in addressing major challenges facing our societies. Last year, in the context of the International Year of Quantum Science and Technology, this colloquium series featured dedicated discussions on quantum science and the broader societal relevance. The series attracted wide interest with more than 2,000 participants and became a valuable interactive platform for exchange among scientists, educators, the policymakers, and also the wider public. Building on this strong foundation, we are pleased to continue the series in 2026 within the framework of the International Decade of Sciences for Sustainable Development. This decade was proclaimed by member states by the United Nations General Assembly in 2023. It started in 2024 and it will last until 2033. And we consider this decade as a transformative era, actually, to bring scientists, policymakers, all different stakeholders in order to show the real value of science and build a culture of science. I mean, the ultimate goal of this decade is really to build a culture of science, which we hope to achieve with your help and with all the help of all scientists around the world by 2033. And this year in July, we are celebrating the first global conference on the International Decade of Sciences, where we will launch the first global report. And in this report, we saw important information on how the science should be done in order to advance the achievement of the Sustainable Development Goals. At UNESCO, we see basic sciences, and UNESCO is the only United Nations agency with mandate on fundamental sciences. We see the basic sciences not only as a foundation for discovery, but also as a critical enhancer of solutions. Physics continues to shape progress in areas such as energy, climate change, climate science, health, digital technologies, and sustainable development. And today's colloquium is therefore particularly meaningful, as we are honored to welcome Professor Stephen Shu, whose career has brought together outstanding scientific achievement, public service, and a deep engagement with science and climate challenges. So I would like to warmly thank IUPAP for this continued partnership, and Professor Shu for joining us today, and we look forward to another fruitful year of collaboration with IUPAP. We warmly welcome all participants today. And now allow me to give the floor back to Christine or to Laura to continue the discussion. Thank you very much.
Thank you, Amal. I'm Laura Green, and I'm here to introduce Stephen Chu. I think we've heard a lot of introductions already. I know him
Laura,
from...
I was planning to say a few words about IUPAP.
Okay.
But I'm going to be very brief. I'm very happy on behalf of IUPAP to start this new season of the series of colloquia on Physics for Society. IUPAP is the only international scientific union which covers all areas of physics. As already mentioned this year, the series of colloquia will focus on the themes of the International Decade of Sciences for Sustainable Development. IUPAP was created in 1922 and now has about 60 territorial members from all over the world. And with this series of colloquia, we expect to fulfill our mission to assist in the development of physics and to help in the application of physics towards solving problems of concern to humanity. I invite you all to visit IUPAP's website to learn more about the Union and the future colloquia in this series that we expect to have 3 more in 2026. Thank you all, and thank you, Professor Chu. Dear Laura.
Okay, well, we're running a little behind, so I'm just going to say I've known Steve for many years, both through Bell Labs and through AAAS when he was president. He was Secretary of Energy for under Obama, and he's the Theodore and Francis Professor of Physics and Applied Physics at Stanford University. And I could go on forever and ever, but frankly, after Alcé won the 1997 Nobel Prize for Research while at Bell Labs, I think I just want to have Steve take it so he has as much time as possible. Steve, it's a pleasure to introduce you. Take it, Steve.
All right. Can you all hear me? Good?
Yes, thank you.
All right. So I'm going to share and share and go into presentation mode. Good. So I'm very glad to talk about the challenges and opportunities in order to get to net zero greenhouse gas emissions. Let me just begin by saying that the original UN goal of staying below 1.5 degrees since the beginning of the Industrial Revolution is now past us. This is a history record from 1850 to 2025. And you see we're definitely over 1.5 going to 2 degrees. But I want to stress 2 things. First, the changes we see today in our weather are not what we've already bought into. And the reason is actually quite simple. 90% of the additional heat that we absorb from the sun goes into the ocean, of which roughly half of that goes into the deep oceans. And it takes a long time to do thermal mixing of the deep oceans with the surface of the ocean. And it's the temperature of the land and the surface of the ocean that dictates our weather. So it's estimated at least 50 years, probably about 100 years in order to, if you don't have any additional warming, just to reach the next thermal equilibrium. So think of the oceans as being a huge heat sink, like a bunch of ice cubes in a glass. And until you melt the ice cubes or until you warm up the ocean, the weather is actually moderated. So that's one of the scary things. So what we see today, I'll say it again, is not what we've already bought into. It's as if you were smoking cigarettes for 30 years, you stop, but you set a chain reaction of things that eventually could give you heart disease or lung cancer 50 years from today. All right, so where are we heading? Well, we don't know because we don't know what the world is doing. So these are several scenarios of what might happen. We're about here, 2025, 26, 2023, this is a little out of date. We are emitting 53 billion tons of CO2 equivalent, over 40 billion tons of CO2. But if you add other greenhouse gases like methane, N2O, hydrofluorocarbons, you get to something above 50 gigatons. Now, the current policies are stated as those pledges from the COP conferences. And unfortunately, most countries are not on schedule for meeting those pledges. But let's just assume that maybe in the near-term future, we can get to current policies. The 1.5 and 2 degree pathways have to go to net zero by the end of this century, and that is extremely unlikely. So it looks like we're heading to roughly 3 degrees, unless something dramatic is going to happen. One of the things that is very important that's not often stressed is that, let me just make this go away, more disappear. No, never mind. I did something bad. Now I have to undo it. Okay, sorry. So what this means on the y-axis, you have to actually go to net zero in everything. So what does net zero in everything means? Well, this is a rough breakup of where greenhouse gases are coming from in various sectors, industry, forest, agriculture, transportation, buildings, and so on. So going to net zero means you have to eliminate the emissions of greenhouse gas emissions in steel, concrete, plastics, chemicals, textiles, the entire food supply chain, which can be over 20% of the greenhouse gas emissions of the world. And I want to stress we need to change from this use once, throw it away mentality that goes well beyond paper or plastic bags. Appliances like refrigerators, which used to work for 20 or 30 years, now they have something like a 7 or 8 year warranty. And remarkably, they break within 8.5 years. And then you're faced with the thing, do you want to replace the compressor or whatever thing that broke or get a new one? But if you get a new one, you get a new warranty, whereas you don't get much of a warranty in the old one. So we're nudged into replacing things, and all this stuff goes into landfill. I should also say that buildings should be made to last hundreds of years, not 50, 70, 80 years, which is what is being done today. And the goal is to prioritize. You reuse. You drink water out of a glass, you wash the glass. You want to repair and rebuild refrigerators, automobiles, things. And it's the last thing you can do before recycling. This is an example of some iconic buildings in the United States. And when they were built, all of these buildings were recently renovated. The hope is that they will be useful for at least another 100 years. And one of the remarkable things about buildings is you can build a building where the HVAC systems, air conditioning, things like that, communication, they can be modernized in small service areas in between floors, and you let the shell of the building last forever. The tragedy is when you destroy a building, the only things that are really recoverable are the steel and the copper. The concrete can no longer be used for structural concrete. The glass is gone. Everything is gone. So we want to build buildings that last hundreds of years. In fact, Europe has led the way, and there are parts of old England, structures, including homes, offices built of wood that are 1,000 years old. All right, some good news. The full cost of electricity, that includes the capital investment, the maintenance, the repair, the land use, is going well below that of fossil fuels. And this red line at 5 cents a kilowatt hour is a very low end range for fossil fuels if you have access to natural gas prices in the United States or the Middle East. But you see that, for example, photovoltaic and onshore wind are becoming very, very inexpensive. And there are already some parts in the Middle East where you can contract to buy electricity at 1.5 cents a kilowatt hour versus the natural gas floor of somewhere around 5 cents a kilowatt hour. It's fantastic news. But I would also say we need this fourth industrial revolution, but the full cost of renewables is not just the levelized cost of electricity, because as you go more and more to renewable energy, you need enhanced transmission, distribution systems, you need backup generation, you need energy storage. And so let me talk a little bit about energy transmission. This is an example of a 1.1 million volt high voltage DC transmission line in China. You may not be able to see, but these little things over here are people. And let me see if I can get a laser pointer. No, it doesn't matter. Maybe you can see this. Anyway, you can see my cursor. These are people. This is a huge thing. And what limits the size of this is not the size of the standoffs between a ground structure like the tower and the high voltage transmission lines. You go much higher than this and you get corona discharge. And so it's going to be limited by that. Okay, so in addition to this is very weird. Sorry about this. Let me see if okay, something's happened. Anyway, just to remind the electrical engineers and physicists and other scientists and engineers who are listening, the power transmitted scales as the ohmic losses, which scales V squared over R. R is the resistance, V is the voltage. So doubling the voltage means you go to 4 times the power. And then DC transmission is much more efficient, less than AC transmission for a variety of reasons. But you can't use DC transmission underground, undersea, because of the coupling to the water or the ground. So then you're limited to far less voltages. Now, if you compare this to chemical transmission of energy, a major gas pipeline can transmit over 50 gigawatts versus this world record of 12 gigawatts over here. So you should always remember that transporting chemical energy, oil, natural gas, has a far higher power flow than the best state-of-the-art high voltage supplies we have today. All right, so what are people doing in anticipation of electrification, in anticipation of continuing lower prices in wind and solar? Europe is beginning to, let's see if I have Europe is beginning to have inter-country transmission lines. The red ones are planned under construction, so you can, for example, take a lot of the energy from Iceland and bring it over here. A lot of the hydropower from Norway and bring it back to the continent. China has the most extensive high voltage AC and DC lines, and these are the existing ones at 2020. And you've got to compare this to the United States, where essentially we have very, very few high transmission lines in the United States. We make energy locally, we use it locally, and there have been some attempts at trying to make a long distance back high voltage DC line, but it's fought by people who have cheap electricity. For example, when I was Secretary of Energy, the citizens in the state of Washington and Oregon didn't want cheap energy going to California or going to Chicago. Similarly, once New England didn't want cheap hydropower coming in from Canada because the people in this metropolitan area down here had already invested in natural gas turbines and they didn't want a stranded asset. So there's a lot of politics in what we do in energy. And in fact, energy is really essentially about money. All right, let's talk about energy storage and grid stabilization. This is my favorite battery. The way it works is when the wind blows or the sun shines, you do the energy intensive task, which is pumping water out of a ground well and putting it in a storage tank. You want to irrigate your crops, you open up the water valve, and so that you can use the renewable energy when it is available. Up until 2015, pumped hydro storage, that is pumping water up to the top of a dam and having a holding pond in the bottom of the dam, constituted roughly 95% of all energy storage. But that is rapidly changing. By 2024, you see that grid scale batteries are catching up, becoming comparable. And the plans are by next year, China wants to increase battery storage to 180 gigawatts of power and corresponding energy storage of hundreds of gigawatt hours. Most of this energy storage is very short term. It isn't even for overnight. And so getting to overnight is well within our grasp, and it will happen within the next 5 years. But seasonal storage is very different. If you use a battery once a day, you can recoup its investment losses. You use a battery once a week or once a month, it's very hard to get the cost of batteries to where it would be. Okay, so here's a typical problem. This is from a record in California. We have a lot of solar. California has 70% non-carbon sources of energy. And in the middle of the day, at noontime where my cursor is, our solar power is beginning to get in excess. So these are times from 2018 to 2024. By 2026, we're further down. And so what do? You use batteries to store this energy, and then you release the energy somewhere between 4, 5, 6, or 7 o'clock, where the peak air conditioning in California is the highest. And so that's what's happening. But again, this is an amazing amount of battery storage in the last couple of years. But China's really talking about factors of maybe 20 more. The good news is that we have cheap solar, cheap wind, going to get cheaper, maybe a factor 2, but it's the batteries that are now important because you want to have access to power. And IRENA just came out with a study called 24/7 renewables. And they asked the question, suppose you want to have access to electricity anytime you want it with 95% reliability. How much will it cost? And you show in different regions, blue is the United States, red is China, green is Brazil, and so on and so forth, the different countries' locations. And we see that from 2020 to 2025, 2035, you get this amazing cost, 95% accessible renewable energy will be about $33 a megawatt hour, or 3.3 cents a kilowatt hour. I live in California in Palo Alto, get our electricity from PG&E, and I pay about 30 cents a kilowatt hour for the least use. We don't have hot tubs, we don't have air conditioning, we don't have anything. So we are don't use very much electricity at all, and we're paying 10 times as much. Anyway, other forms of energy storage, hydrogen comes in different colors. Gray hydrogen is you mine methane, you recover methane, natural gas, and there's a process where you can convert to hydrogen and you vent the CO2. And that's the current cost today for natural gas, around, I think it's $4 a million BTU. Blue hydrogen is okay, but it's not the cat's meow, because the fact that you're recovering methane means that you're disturbing the ground, and there's leakage from the ground as well as from natural gas distribution lines. The best is if you can make hydrogen on site electrically where you want it, so you don't need a distribution system, but the price is well above 4 times what the gray hydrogen is. And so the hope is that you can get to $2 production site, maybe even $1. Hydrogen is very useful, not only as a heat source and energy source, but it can be used to decarbonize steel, plastic, chemicals, and so on. There has been a lot of progress made in getting much more efficient catalysts using much less precious metals, and so that's working. But I want to stress that hydrogen is very leaky, and we cannot detect hydrogen optically. It's a symmetric molecule, and if you have a pipeline, you can't detect leaks, you've got a real problem. So pipelines, you can't have hydrogen pipelines unless you can get a drone flying very close to the pipeline and uses mass spectrometry to actually see if hydrogen is in fact leaking. Again, no optical signature. There is a possibility, very experimental, yet to be proved, that if you can have iron deposits deep underground that are quite hot and you mix water with it, you can change the oxidation state of iron from Fe2 plus to 3 plus, and you can get out hydrogen. We don't know how much this is going to cost, but some of the most optimistic estimates are maybe half a cent a kilowatt hour to a cent. $1 for a kilogram of hydrogen. All right, let's talk about electrification. There are EVs and IC as internal combustion engines. This is the forecast. We're now over here, and this forecast, I'd like to show this because it was an optimistic forecast of 2022. Internal combustion engines sales still are higher than EVs, except in China, where you would have to wait 2 years in order to get an internal combustion engine car. But if you want an electric vehicle, you can have one immediately. So this is delayed, and with the current U.S. administration in the United States, it's further delayed. There are no subsidies for EVs today. And so the charging time, I used to say that if we can go 300 kilometers in 5 minutes, EVs will dominate the market. What about the battery technology? This is the energy density per unit weight, energy density per unit volume. And it's remarkable. I used to think the energy density would be up here, but I was wrong. We're now at 2025, and we're on the board of directors of a battery company now selling batteries at 450 watt hours per kilogram. And it's up here, and that was 2 years ago. So the progress has been great. What about the cost? Well, the cost has plunged. This is on a logarithmic graph going up to $500,000 per kilowatt hour of energy storage. Every time you increase by an order of magnitude the number of product deployed, the price goes down exponentially. And this is called what's a learning curve. And so what is happening over here is that Tesla and other manufacturers are beginning to use batteries in a very big time way. And once that has got established, you see the price continue. There's no way to predict the slope of the learning curve, but remarkably, once it's established, it stays there for decades. And so this is just a summary of how much battery prices have plummeted. And one way to break this learning curve is if there's a resource allocation problem. We used to be worried about lithium, but now people have developed methods of extracting lithium out of salty water. You go drilling for oil and gas, you produce a lot of salty water, and it's very rich in lithium. In fact, the lithium in the water that you produce in the oil is worth more than the oil. Cobalt is already too expensive. Nickel's getting there. And so the batteries for EVs are now iron phosphate. They've already transitioned. In 100 years, we could look for an increasing shortage of copper, especially with the increased electrification. So what does the shortage mean? It means the price of copper goes up. So to the young people in the audience, if you think about making a conductor, let's say out of carbon nanotubes that can be competitive with copper, the conductivity per unit weight of a carbon conductor, like a nanotube, is far higher than copper. And there's so much more. There's orders and orders of magnitude more carbon in the ground than we have copper. So this is a possibility. But anyway, these are the material shortages. Let me tell you about the EVs. I test rode in a Xiaomi SU7. This one costs $42,000. It has 438-mile range, and it can charge over 200 miles in 15 seconds. And it accelerates 0 to 100 kilometers per hour, is roughly 0 to 60 in less than 2 seconds. Why anyone want to go that fast, I don't know. The flesh on your face pulls backward when you stomp on the pedal. This is a beautiful car. It looks kind of like a Porsche because they hired the Porsche body designer to make it look like a Porsche. But, there's been progress, and BYD just recently, in the last couple of months, introduced a battery that they claim will add 250 miles in 5 minutes. Now, at that point, let's say you drive 250 miles on an interstate, you want to charge. So you plug in, and while you go to the bathroom and are discharging, your car is charging. It takes roughly the same amount of time, and so everybody's happy. But so this battery technology is leaping ahead, very, very exciting technology. Although I should say, in order to charge this fast in this shorter time, it requires a 1 megawatt connector. And the Tesla connectors go up to, I think, 350, 400 kilowatts. All right. So we talked about hydrogen production, but let's talk about electricity demand. We talked about electrification of transportation. There's going to heat pumps rather than gas burning space heaters, things like that. And the data center growth is non-trivial. In a paper written in 2015 or so, they were projecting that the demand in electricity would go from 35 gigawatts in 2024 to 78 gigawatts by 2025. And so that means the fraction of electricity used by data centers, telecommunication, and things like that will more than double. Now, why are the data centers and the AI and the machine intelligence doing all these things? Well, they're using a bazillion parameters, 10 to hundreds of billions to even trillions of parameters for deep learning models and to make sense of a vast amount of data. But you have to compare this to, let's say, a young girl, a 4-year-old toddler on the left, and this person can tell the difference between cats and dogs, one of the first triumphs of machine learning. It can learn 3 or 4 languages. If the mother speaks one language, the father speaks another language, and a living student speaks a third language. By 4 years old, they're fluent in all the language, and they can translate between all the peoples. And they do it on orders and orders of magnitude less data. And on the right, you have a young man doing some physics experiments, deciding that gravity makes food fall down, not up. And how much power? Instead of a gigawatt of power, which is the new data centers are using, you're using about 35 watts of power. Very different architecture. Can we imitate this? Maybe, maybe not. Probably not, because in a human brain, one neuron can talk to 1,000 and up to 10,000 other neurons, and we don't have that interconnectability at the moment. Okay, so even with low-cost electricity, we still need some compact turn-on sources. There are certain parts of the world who don't have enough land, don't have access to onshore wind. Offshore wind is still very expensive, especially deep offshore wind. And so if you want a compact turn-on source, you have to make a choice. There's coal or natural gas, then you'd have to capture and sequester or use the carbon dioxide. Or we have nuclear fission, and then you have to dispose of the fuel. In terms of the safety, there's no comparison. If you look at the deaths per unit electricity energy being produced in terawatt hours, anytime you burn coal, brown coal, or normal coal, black coal, oil, even wood chips, biomass wood chips, these are the deaths that are incurred. And whereas nuclear is down here, it's a little bit safer than wind and solar, but wind, solar, and nuclear, in terms of deaths, including Chernobyl, there were anticipated a couple hundred more premature cancer deaths from Fukushima. If you include all these nuclear accidents, it's still much, much safer. What's the problem with nuclear? The problem is we forgot how to build reactors on budget, on time. In this graph between 1970 and 2025, we see the cost of reactors going through the roof. In US, this is 3 Mile Island, Chernobyl, and the Vogtle 3 and 4 plants are way up here, roughly 4 or 5 times more. The French reactor is also way up here. So how is China able to build nuclear reactors on budget, on time, and have a learning curve? And it's not rocket science. They use the same crew, same design to build one reactor. They move the crew over, build the same reactor, exactly the same crew. And you do this over and over again, and the price goes down. In fact, the difference between Vogtle 3 and Vogtle 4 was about a factor of 2, because the same crew finished after building Vogtle 3, built Vogtle 4. So common sense will actually allow you to build modern nuclear reactors that could last 80 years instead of 40 plus 20 years that we have in our current fleet. And so this is possible. What about storage? There are new technologies in storage. I'm associated with this company, Deep Isolation, where you drill down and then sideways, and you put the radioactive storage in canisters. So you don't need any of the infrastructure of tunnels and ventilation and everything like that in order to dispose of it, where before you had to build tunnels to drive trucks and lay the thing in. Now you just put it in a canister and slip it under the rock. And so this is now being tested in several countries in Europe as well as in the United States to prove that this is a viable way of getting much cheaper storage. Perhaps the difference between manned and unmanned spaceflight. Will commercial fusion be deployed commercially? I don't have the details of going into it. This is my estimate of when commercial fusion will be available, somewhere between 30 years to never. Why never? Well, because we have not solved the neutron damage problem. And neutrons will displace atoms. And in a commercial fusion reactor, the atoms will move 50 or 100 times per year, and alpha particle creates helium bubbles, and the material just falls apart. This we have not solved. In order to have commercial fusion, you need to solve this materials problem. Okay, I'm at time, so I'm just going to mention very briefly, we need a fourth agricultural revolution. The first two agricultural revolutions were domestication of plants and animals, things like that. But the third one was being able to make nitrogen-based fertilizer, and also the crossbreeding of crops led by Norman Borlaug and others. Haber and Bosch got 2 separate Nobel Prizes for their Haber-Bosch prizes. Norman Borlaug got a Nobel Peace Prize. The agricultural revolution was fantastic. Between 1961 and 2021, the population went from 3 billion to nearly 8 billion people. The amount of land put under cereal production, wheat, corn, grains, things like that, remained the same, whereas the productivity per acre increased dramatically. What's the problem? The problem is we use fertilizer. When absorbed by the plants, is great. But when it's not absorbed by the plants, other microbes in the soil turn it into N2O. N2O is a greenhouse gas, much worse than CO2, and lasts 100 years. So how are you going to feed 8.5 billion going to 9.5 billion by mid-century without fertilizer? And so there may be a way of doing this using synthetic biology, and that is you can introduce microbes to enter into symbiotic relationships with the crop you want to grow. In this case, it's corn. And a company called Pivot Bio collaborated with a synthetic biology company, Zymergen, to actually do this. And what these companies did is they could eliminate half the fertilizer of corn. But the problem is the development time was 8 years. And the synthetic biology company went bankrupt because it couldn't develop the microbes fast enough. And so there's work, including my own lab, to try to get much faster search for the genes, which requires putting in larger pieces of DNA into the microbes to hunt around for good solutions. All right, finally, we're likely to go over 500, maybe even 600 parts per million. And so we'll need to capture carbon dioxide, not only from the sources of carbon dioxide I already mentioned, like plastic, steel, chemicals, but also we need to capture things because of the N2O emissions. And so right now, the cost of capturing carbon and then releasing it 1 atmosphere, if it's reduced to $100 a ton or $150 a ton, the world will use it. But it's nowhere near that. It's more like $800 a ton for direct air capture. And so we're going to need this. And I think in the coming decades, we'll need to capture at least several to 10 gigatons of carbon dioxide equivalent per year because of these hard to abate things, especially agriculture. If you compare the amount of volume to this, all of landfill around the world is 2 billion tons of solid waste. And so we're talking almost a factor of 5 or 10 more storage for carbon dioxide. Carbon dioxide storage capture is way too expensive. This is the first plant that came on budget on time, but it costs $1 billion. and captures maybe 25% of a large coal plant's CO2. This is not sustainable. It's huge. The footprint of this is 1 acre, again, to capture 1/4 of a coal plant in Louisiana. That's a large pickup truck. And so if you look at the basic physics of taking CO2 from 400 parts per million or 500 parts per million to 1 atmosphere, so you can capture from air and then release in 1 atmosphere, you can then compress and sequester it, or maybe turn it to something useful. The minimum requirement due to the second law of thermodynamics, entropy of concentrating CO2, is 20 kilojoules per mole. And right now, the current methods are 25 times more energy, have more energy use. And so there's plenty of room to improve. In my own research, we spun off a company, and we're hoping that we can get this down to maybe 4 times this cost rather than 25 times the cost. And we're shooting for $150 to $100 of air capture. Okay, so in conclusion, let's look at energy transitions. In the United States, when we transition from wood to coal and coal to petroleum and natural gas, and you look at the width of this, it looks like it takes about 60 years to make this transition. Now you're beginning to see hydroelectric, nuclear, other renewables. And the question is, well, take another 60 years. But you should also ask, what is the rest of the world doing? And what we found is whenever you have a new source of energy, like wind and solar, you just add to the older sources of energy, because the appetite for energy around the world is huge. If you're a developing country, it's directly related to the living standard and prosperity of the country. And so this is where we're going. You see that the transition in terms of energy being created from all these sources of energy, and just the stuff we were talking about is just a little sliver up here. So in conclusion, I think we are heading to about 3 degrees, maybe worse, as if you're on the Titanic and you're full speed ahead, not realizing that there's an iceberg ahead. Now, in the movie Titanic, you may recall that it did not turn on time. And so in this movie, the one we're currently in, I will stress that it will take at least a half a century to decarbonize from where we are today. And so from that, I will end and stop sharing.
Thanks a lot for those outstanding insights. So indeed, so now time for question. Laura.
Yeah, so why don't we ask, we have 2 questions from UNESCO and 2 from IUPAP. So Amal, why don't you ask the first UNESCO question?
Thank you. Thank you very much, Laura. Thank you very much, Professor Shu, for this amazing and really insightful presentation. So my question will be related to perspective of UNESCO regarding science policy interface. And you have worked both at the forefront of scientific discovery and also at the highest level of policy making. So looking ahead, and within the framework, for example, of the International Decade of Sciences for Sustainable Development, what do you see as the most important role that scientists should play in helping societies address complex global challenges such as climate change, energy security, and sustainable development?
Okay, so the most important thing is that the scientists and engineers can develop better technologies. I think within 10 years, the EVs will be better than internal combustion engine cars in every way, including the fast charge. I mean, right now, there's not an adoption in many places around the world because there's range anxiety. If you can go 200 miles in 5 minutes, you go back to a service station model. And that means you drive and then you just go another 200 miles, and people are not going to be really put out of shape, I don't think, that they can't go 400 miles in 5 minutes. They can only go 200. But that is becoming a reality. And the cost of EVs is plunging. And so, except in the United States. Now, in the United States, we're projecting U.S. car industry by 100% tariff on any Chinese automobile. So there are no imports. And so this is a real problem. Huge tariffs, protectionist tariffs like that tend to discourage innovation. And so I'm very worried about the U.S. auto industry. If they get all this protection from competitors, there's no need for them to improve. But in the end, unless they make better cars, there's some. So going back to the low-cost things, I think batteries and solar will transform the world. If you have batteries, especially batteries that work in hot temperatures, utility scale batteries that don't need a controlled environment. Tesla battery can't get that hot, otherwise the chemistry just goes south. It gets ruined. And so there are such batteries. There are sodium batteries that look like this. There's huge effort to get batteries that can work in freezing cold and really high temperatures, 60 degrees C. Operating at 60 degrees C. And I hope we don't go to 60 degrees C in the next couple of decades. Wow. But that will transform the world, because just like cell phones, you don't need a wired connection anymore. And you can be in rural areas, you can be non-rural areas, you can be developed areas, and you can pop these things in. Compared to the cost of diesel generation, I'm very optimistic about this. And so the best thing scientists and engineers can do is improve the technology, make it better than what exists today. And once the technology is better, then you don't need any political will. People will just do it.
Thank you. Thank you so much. Yes.
Laura. So Vina, do you have a question from IUPAP?
Thank you, Laura. We had a question on AI, but that was responded during the talk, I would say. So let me move to the second question, which is two in one, actually. If you had a 10 billion research portfolio, what fraction would go into basic research versus strengthening our existing technologies? And then focusing in physics and looking into the future, 50 years ahead from now, what research do you think we should have invested in that is neglected at present?
Okay, so my attitude towards what to fund in, let's say, federal dollars, federal level, is no different than when I was Secretary of Energy. I looked around and I said, if industries really got their hands on things, as they get wind turbines, there's really not that much need for us to put in hundreds of millions of dollars into wind turbines that commercial companies are doing. I'm beginning to think that is also true of batteries. However, batteries are such a crucial part of this, and what we need are batteries that are non-flammable. They could be gigawatt hour, gigawatts and gigawatt scale. We had a terrible battery factory, I think, in the state of Washington, which is a gigawatt power battery. Highly polluting, disaster. And so we would need, for example, aqueous batteries. That is, instead of standard lithium iron phosphate electrolytes, which are flammable, if the carrier of the ions, zinc, iron, for example, then if it's water, it won't catch fire. And so in my own lab, I'm trying to do this. Now, the downside of an aqueous battery is you begin to split water after about 1.4 volts. And you're making hydrogen oxygen. You want it as an energy storage mechanism. And the cost of batteries is actually a large fraction is the real estate. So you want a battery works at 3.5, 4 volts. So what we're doing is we're saying, okay, can we design a layer that's maybe a few microns thick, that's in between the electrodes and the water, so the ions can go through, but the water can't. So the challenge is water is a pretty small molecule. And our first attempt at using Teflon, something that repels water, and polymers like that failed. There's still a little water that got through into Teflon. And so we're now going to what are called solid state electrolytes, where the ions actually hop from defect to defect, and there's such a small pace that the water doesn't get through. So we'll know within 6 months whether this idea is going to fly or not. And if it does, it can be scaled because the same solid state electrolytes that the EV industry wants to use, they want that for safer car batteries as well. So that's where it stands. And so there are many, many things like this but I think it's going to be transformative in the same way that mobile phones were transformative. Yeah. You want to get energy to poorer people very quickly.
Thank you. Amal, do you have another question?
Yes, one more question, please. Thank you very much, Laura. So, Professor Shu, you have often emphasized the importance of evidence-based decision-making. At a time when scientific evidence is sometimes questioned or politicized, how can scientists and the scientific institutions strengthen public trust in science while preserving their independence and credibility?
Well, I think scientists have to remind the public where would we be without science over the last couple hundred years? And in science, I include, all the things in the Industrial Revolution were, actually coming from lots of engineering possibilities, materials, things like that. The ability to make optical fibers so pure that you can send it long distances. The whole computation and internet is based on that. And there are diseases that even as short as 10 years ago are fatal are now turning into chronic diseases. There are a number of cancers that are turning into chronic diseases. So it doesn't kill you in 5 or 10 years. You can last for 20, 30 years. And so we have to remind people that all this came out of basic research. And you do not want to shift the funding away from basic research. You want to pay very close attention and hoping that there'll be enough incentives and other means to encourage companies to take up the investments. I'll give you one trivial example that has nothing to do with technology, but when I was Secretary of Energy, I was heavily criticized for the loan program. We loaned to Tesla. We didn't loan to Tesla. It didn't announce the loan in the beginning of 2009. It would have gone bankrupt. And EVs would not have progressed the way they did without Tesla. Wall Street would not invest in billion-dollar solar wind farms. They said it's too risky. 100 million, maybe, not $1 billion. We invested in $6 billion wind and solar farms. The program ended in 3 years. And after that, Wall Street said you can make a lot of money this way. And so then they invested in it. So you want to show private industry that you can actually make a business out of this. And so what scientists and engineers is improve the technology, and then you have to demonstrate that it's better. When I was Secretary of Energy, I often quoted Sheikh Yamani, who's a former Saudi oil minister. And he said, the Stone Age did not end for the lack of stones, and the oil age will not end for the lack of oil. So what do you mean by that? He meant you come up with something better. You go from stones to metals, and they're better, and people will make the transition. You go to energy that's better. Energy that you can make in your own borders that give you energy security is going to be better than shipping oil and gas around the world. And so these are the things. So you make it better, and if it's made better, then the shift is very quick.
Thank you. Thank you so much, Professor.
Thank you very much. I have we have only a few more minutes left, but there's at least 2 questions I want to ask from the audience. One is that you didn't bring up fusion. So the question from Dejanovic is, how do you see the balance between long-term fusion research and near-term advanced nuclear technologies, such as thorium-based systems, in achieving climate and energy goals? And if you want to make it more simple, do you want to balance fusion energy research versus fission energy research?
My feeling is that the investments in fusion research are small compared to the problem we're addressing. Mm-hmm. So I'm all in favor of fusion research. There's the Cellular in Germany is going great guns. Within a year after just turning on, it worked. But you have this neutron damage problem. And only recently are people actually trying to develop the high energy neutron source to actually start playing with materials that don't crumble as easily. Yeah. But I have great confidence that the plasma physicists will make these plasmas stable. The accelerator is going to be a CW machine. That's not what I worry about. Material science is totally different. We're not where we can use quantum mechanics or whatever to make a better material. It's shake and bake. You try it and see it works. You try it and see it works. And so we need to do that until we get to the point, perhaps with quantum computers, where you can actually design ab initio. But so far, it's not true. So
I love your, yeah.
So anyway, so yes, invest in fusion. It's a small drop in the bucket for all the costs of not mitigating climate change and the cost of adapting to climate change are huge. So it's a nothing.
I love your attitude, and certainly Fermi had a big impact on material science when he was developing reactors. I have one more question, which I really like here from Heather Cicerone. How do you see a role for the humanities to participate in the energy transition sphere? How can writers, artists, and other creative workers help to support the efforts of scientists?
Well, a lot of it is convincing people of two things, or three things. One, we do have a problem. And sometimes most scientists aren't the best advocates for describing the problem in ways that the public can understand. Another thing is, how do people make decisions? Most of the decisions are very short term. And climate is a 50, 100, or 200-year problem. And we saw this with the invasion of Ukraine. All of a sudden, energy security, topped the list. And climate change, forget it. It's number 10, 12, 15 down on the list. So you need access to energy and you need cheap energy. And that's number 1 and 2 on the list of anybody. And so while you're doing this, again, we have to go back to science. Why should it cost more? And as I said, there's some areas, wind, solar, and EVs where they are getting better. They will be better. And we need to do this, especially agriculture, we need to do this. Now, in the end, there's a huge challenge. If you can get hydrogen at $1 a kilogram, if you can capture carbon dioxide at $100 a ton, and it's pure form of carbon dioxide, then you have the ingredients to possibly search for a way of making it into a chemical fuel, not methane, but methanol. Methanol ships as a liquid. When you ship crude oil halfway around the world in the super tankers, it adds about 1 cent per gallon to your cost of gasoline. Wow. Only a penny. Okay. Maybe 2 pennies now because of the Iran war, but it's a nothing. And so to be able to ship liquid material nominally at room temperature is a huge deal. Yeah. And so that's an open question. How do we make methanol, ethylene, other things to replace the fossil base that we use today? If we can do that, then we're in a very good position. But I go back to a lot of things even in developing countries. The Iran war that the U.S. started tells us that you want to have access to energy, ideally on your own shores. The first oil embargo of the 1970s, 73, 74, 75, where we ran, the supply was cut and there were long gasoline lines and things like that. And so now, because of that, the developed countries have a few month oil reserve supply. China has 6 month oil, but 6 months is nothing in the overall scheme of things. And so that's why I like either fusion or fission. Fission, you can have years on your own borders. You can do this with coal. You can't do this with natural gas.
Right. Fascinating. I think we don't have that many more questions, and we've answered so many things. What I'd like to do is, first of all, thank Stephen Chu once more time, and then ask Silvina to do a wrap up. And this has been fantastic. Silvina, take it.
Oh, thank you, Laura. I'm just going to be very brief. We thank very much Professor Chu for this enlightening talk that I found quite optimistic. So I'm leaving the floor with the idea that things will be solved or at least leveled, and we are not making it worse. And so I want also Christine to close this session, inviting everybody to watch the next colloquia in this series. And thank you again, Professor Chu.
Yeah, thank you. Thank you so much for this very inspiring event. So we really sincerely thank you for your presentation, so Professor Stephen Cho, and for this outstanding and inspiring insight that you shared with us for those challenges that are facing in the humanity. So many thanks as well for the panelists that we have and for the question as well for the audience. There was a lot of questions indeed. We saved all of them as well. So I think it's very inspiring and interesting to see. So, and we really hope that the discussion continue beyond as well this session. So as this is a transition for the net zero greenhouse gas emission, this requires a really sustainable dialogue as well. So finally, we want to save as well the date for you so that in September, the 3rd of September, at 2 p.m. Stockholm time, so there will be as well the possibility to listen more, and we will look forward to welcome another distinguished speaker for new perspective as well on science for sustainable development. So thank you everyone for attending, and thank you very much, Sir Professor Cho.
Hey, thank you all.
Thank you very much.
Thank you very
Bye,
much.
everybody.
Bye-bye.
Bye-bye.
Bye.
Bye.